Okay, so now let's see another very important example of groups called the symmetric groups. Or also known as permutation groups. Okay, so we are given a set X. Sx, the symmetric group on X, as a set, this is the set of all bijections sigma from X to X. So recall, bijection, this means injective plus surjective. In case X is finite, it suffices to check one of these two properties to have the other one for a self-map from X to X. But if X is infinite, you might have one of these but not the other. Okay, and the case that we will consider most in this course is when X is finite. So an important special case is when X is finite, and then here we are just using the structure of X as a set, so we can write X, just take the set with n elements, 1 to up to n, and in this case we write Sn for S sub X. All right? So let's check again that Sx is a group. So we have to check that it's closed under multiplication. If we have sigma and tau in S sub X, that is, sigma is a bijection from X to X, and then tau is another bijection from X to X. We think of these as functions. So the product sigma tau, if consider sigma tau, which is the composition sigma composed with tau. So we should do tau first and then sigma. And now we want to see that this is again a bijection, and that is clear because tau and sigma are both injective. The composition sigma composed with tau is also injective, and then because tau and sigma are both surjective, their composition is also surjective, so it's bijective. Okay, good. So sigma tau is closed under multiplication. Now we have to check the identity. So the identity permutation, permutations will be another name for the elements of these symmetric or permutation groups. The identity permutation is, I will often write it E as the identity of a general group. It is the function from X to X that fixes every element. So E of little x is equal to little x for all little x in big X. And inverses Inverses, well, as you know from when you learned about functions, the inverse of a bijection is again a bijection. So it's closed under inverses, and for associativity, it's the same discussion as what we just did in the case of matrices. It's just associativity of composition of functions. Okay, so the conclusion is that indeed S sub x, the symmetric group on X, is a group. Okay, so let's continue with the example of symmetric groups, and let's do an example of that. Let's look at the case of S3. So that is, we are looking at Sn with n equal to 3, or we can also think of it as though we're looking at Sx with x equal to 1, 2, 3. Okay? So what's going on here? We have 1, 2, and 3. Let me write them twice. Now we want to permute these. So for every element, for every number here, I have to draw one arrow going out and going to the other side. And I have that it be a bijection means I have to make sure that so it has to be injective. So no number here can be hit by two arrows, and that it's surjective is that every number here must be hit by an arrow. So for example, I am allowed to do, this is a permutation where, so if I would want to write this as a function, I have sigma of 1, if I call this sigma, sigma of 1 is 3, sigma of 2 is 2, and sigma of 3 is 1. Now, what is a non-example? If I do 1, 2, 3, 1, 2, 3, if I map 1 to 1, 2 to 1, and 3 to 3, then both the injectivity and the surjectivity are violated. 2 is not hit by anything, and 1 is hit by both 1 and 2. So this is a non-example. All right? So now let's think about how many different permutations of 1, 2, 3 are there. How many elements in S3? By the way, I will write the number of elements as, I will use this notation for the number of elements, and I will also write it like this and talk about the cardinality of the set S3, and similarly for the cardinality of any other set that will show up in the course. Okay, so let's get back to the problem at hand. How many elements in S3? Well, let's look at the picture here. When we looked at 1, we had to pick where it goes. We had 3 possibilities. So 3, these are possibilities for tau of 1. If I have a tau in S3, 3 possibilities for tau of 1. Now 2, where can 2 go? So it can't go to the same place as 1, because then we'd be in this situation and violate the injectivity. But it can go anywhere else. So 2, this is 2 possibilities for tau of 2. And finally 3, once we've sent 1 and 2 somewhere, then there's no choice for 3 but to send it to the last vacant number on the right-hand side. So there's 1 possibility for tau of 3 that's left. And if we multiply these possibilities together, we get 6 for the order or cardinality of S3. Okay? Now, let me write out explicitly the 6 elements of S3, and I'll use this opportunity to define one of the many notations used for describing permutations. There are many different ways to write down permutations. So here's one way to do it. I write 1, 2, 3 on top. If I was doing S5 instead of S3, I'd go up to 5. And then I leave space in the bottom. I have, if you want, it's a matrix with 2 rows and as many columns as the size of the set that we're permuting. And now what I'm going to do is below each number, I'm going to write where it's sent by the function. So if I'm looking at this sigma over here, then I have sigma of 1 goes to 3. So I write 3 below 1. Sigma of 2 goes to 2, I write 2 below 2. And sigma of 3 goes to 1, I write 1 below 3. So this is my notation for sigma. So if I want to do another permutation, I could, for example, do 1, 2, 3, 1, 2, 3. What's going on here? 1 goes to 1, 2 goes to 2, 3 goes to 3. So this is just the identity. And what are the other ones where, well, we can do 1, 2, 3, 1, 3, 2, 1, 2, 3, 2, 1, 3, and 1, 2, 3, 2, 3, 1, and 1, 2, 3, 1, 3, 1, 2. Okay? So here we have 6 elements. Just to make sure that we're on the same page, let's take this last one and let's unpack this notation back to writing it as a function. So let's call this f, and let's say, what does this mean as a function if I want to write f of 1, f of 2, f of 3? Well, below 1 I have 3. That means that f of 1 is 3. Below 2 I have 1. That means that f of 2 is 1. And below 3 I have 2. That means that f of 3 is 2. Okay. Later on we will see a yet more convenient way to write permutations. You will find when you start working with them that this is quite a lot of work to write down all of this, especially when you have more than 3, when you start having larger permutation groups. Okay, finally, let's see a third way, what is, in my opinion, the most convenient way to write down permutations. This is called the cycle decomposition. Okay, so let's start with the permutation written in the way that I just described to you. I'll take a bigger one now, not on 3, but let's say on 5 elements. So I write 1, 2, 3, 4, 5 on top, and then I have to say where each of 1, 2, 3, 4, 5 map to. So let's take, for example, 2, 3, 1, 5, 4. All right, so this is an element of the symmetric group on 1, 2, up to 5, which we write S5. Now, I want to write this in the following way. So I want to write it as a product of cycles, which means it means the following. I open a parenthesis. I take a number on the top, like 1. If it maps to itself, then it will not appear down here. We'll do an example of that later. Here, we check there is no number that maps to itself. So I take 1, I put it here. Next, I'm going to put another number. What am I going to put? Look where 1 maps to. 1 maps to 2, so I put 2 up after 1. After 2, what do I put? I put where 2 maps to. 2 maps to 3, so I put 3 after 2. Okay, now if we would continue in this way, then after 3, I should put what 3 maps to, but 3 maps to 1, which is already here. So the rule is that when you have something and what it maps to is already there, then instead of putting it, you close the parentheses. And that's telling me that 3 maps back to 1. This thing is called a cycle. And then we open a new parenthesis. Now I take a number that is up here, but does not appear in this cycle. So I can take either 4 or 5. It's often a convention to take the smallest one that you haven't dealt with yet. So I put 4 here. Where does 4 map to? It maps to 5. Where does 5 map to? It maps back to 4. So I close again the parentheses. And this is the cycle decomposition of sigma. Okay, let's do another example where this time we will have, I will put on top some elements mapping to themselves. So 1, 2, 3, 4, 5. And then let's have 3 and 4, well, or let's say 1 and 3 map to themselves. And then I'll have 2, 5, 4, 2. Okay. So here's a permutation, again in S5. Okay. So this time I open my first parentheses. And I would like to put 1 here. But oh no, 1 maps to itself. So I shouldn't do that. So 1 is going to be left out of the cycle notation. So I move to the next number, 2. Does 2 map to itself? No. So okay, so 2 is good. I can put it here. Then what follows 2 to the right? It's where 2 maps to. 2 maps to 5. So I put 5 next. Then 5 maps to 4. Then 4 maps back to 2. So I close the parentheses to indicate that the cycle is finished. And then what numbers from 1 up to 5 haven't I considered yet? 3. But 3 also maps to 3, so we leave it out as well. And this is the cycle decomposition of sigma. Okay? And similarly, let's now do an example where we start from a product of cycles and we understand what it means in this notation as which is maybe closer to the original function notation. So let's start with the product of cycles. 1, 4, 3, 2 times 7, 5 times 6, 8. Okay, so here I have a 4 cycle. It means I have a parentheses and I have 4 numbers inside the parentheses. Here I have a 2 cycle. And here I have another 2 cycle. Now, altogether, I've used up here in my 3 cycles, I've used 1, 2, 3, 4, 5, 6, 7, 8. But I can choose to think of this as an element of S10. That means there are numbers from 1 up to 10 that don't appear here. That means those numbers will be fixed. Okay? So now if I want to write this in this notation, I have to write the numbers up to the dimension of this. This is S10. I have to go up to 10. All right. Now, what do I write below 1? Well, 1 appears in this 4 cycle. And I see 1 goes to 4, because 4 is to the right of 1. So I write 1 goes to 4. Then I have the next information in this 4 cycle is 3 after the 4. That's telling me that 4 maps to 3. So I have to make sure not to write 2 goes to 3, but it's telling me 4 maps to 3. Then 3 maps to 2. And then 2 maps to 1. That's because the parentheses is closed. It means return to the start. So that's all. I'm done now with this 4 cycle. Now this first 2 cycle, it's telling me that 7 maps to 5. And that 5 maps to 7. And similarly, the other 2 cycle is telling me that 6 maps to 8 and that 8 maps to 6. And finally, as I said, the fact that 9 and 10 don't appear in these cycles is telling me that 9 maps to 9 and 10 maps to 10. So if we call this maybe rho, then rho is, this is the cycle way, and this is the other way of writing rho. Okay? Now, I should point out one important thing, that in this cycle decomposition, there's one important thing that we haven't discussed, which is that these cycles are disjoint. So the cycle decomposition writes any sigma in Sn as a product of disjoint cycles. What does it mean, disjoint? So if I have 2, 3, and 3, 4 are two cycles which are not disjoint, since they share. So being disjoint means not sharing any numbers, while these two, they share the number 3. They share 3. On the other hand, if I take 2, 3, and 4, 5 are 2 disjoint 2 cycles. Okay. So it's important that when you write your permutation as a product of cycles in this way, you make sure that your cycles are disjoint. If you take the product of these two cycles that are not disjoint, you still get a permutation, but it's more complicated to determine what it is. In fact, you can take this product and write it as a, if you take this product, you will see that it is 1 3 cycle, which is therefore disjoint. If you have 1 cycle, it's always disjoint.